the topic we are going to talk about is monotonicity, or increasing and decreasing functions. Let fx be any real valued function with domain df. Let open interval ab be any subset of domain of f. Then fx is said to be strictly increasing or strictly monotonically increasing. We sometimes leave the word monotonicity. We simply say strictly increasing or strictly monotonically increasing. Then fx is said to be strictly increasing in the open interval ab if x1 less than x2 implies fx1 is less than fx2. That is, as x increases, fx also increases. As x increases, fx also increases. That is, the trend is maintained. As x increases, the values of the function also go on increasing. Such functions are known as strictly increasing functions. In these functions, this trend is maintained. x1 less than x2 will mean fx1 is less than fx2. x1 less than x2 will mean fx1 is less than fx2. Next is strictly decreasing in open interval ab. If x1 less than x2 implies fx1 is greater than fx2 for all x1 x2 belonging to ab. That is, as x increases, values of the function decrease. As x increases, fx decreases. That is, the trend is reversed. In these cases, the trend is reversed. Such functions are strictly decreasing functions. Increasing in open interval ab. If x1 less than x2 implies fx1 is less than or equal to fx2. Here there is strict inequality. Here it is less than or equal to. If strict inequality is there, we say strictly increasing. If it is less than equal to, then we say it is increasing. So for increasing in AB, x1 less than x2 implies fx1 is either less than x2 or equal to fx2. Decreasing in AB. If x1 less than x2 implies fx1 is greater than equal to fx2. x1 less than x2 implies fx1 is either greater than or it is equal to fx2. Such functions are known as decreasing in AB or monotonically decreasing, monotonically increasing. Now graphically, strictly increasing functions. Now as x increases, fx also increases. So as x will increase, fx will also increase. The graph of such function will be of the form this. That is, as x is increasing, fx values of the function are also increasing. Graph of such functions are rising graphs. This is a rising graph. These are rising graphs. Strictly decreasing. For strictly decreasing, as x increases, fx decreases. That is, as x increases, y will decrease. Y will decrease. The graph of such function is of the form this. The graph will be a falling graph. This will be a falling graph. If it is a strictly decreasing, it will fall strictly. And in case of increasing functions, the graph of the function is for increasing functions, it is less than or equal to. So graph of such functions is rising or remains at the same level. It is rising, remaining at the same level, and again rising. So such graphs are either rising, rising or remains at same level. It is either rising or remains at the, here it is rising, here it is remaining at the same level, and it is rising again. So graph is of the form this. It is nowhere a falling graph. It is either increasing or remaining at the same level. And for decreasing functions, the graph must be of the form, it is either falling or remains at the same level, and it may fall again. The graph must be falling or remains at same level. It must be a falling graph or it must remain at the same value. These two values must be equal, can be equal. So what we observe is a strictly increasing function is also monotonically increasing, because for monotonically increasing function it must be less than or equal to. For strictly increasing functions it is less than. So this condition is satisfied. So strictly increasing function is also an increasing function, but converse is not true. If it is increasing in AB, it may not be strictly increasing, because here the values can be equal. For strictly increasing functions, value cannot be equal to fx1 cannot be equal to fx2. So an increasing function is not strictly increasing, but a strictly increasing function is always monotonically increasing also. And similarly for decreasing function, if it is strictly decreasing, it is also decreasing, because here one of the two conditions must be satisfied. Either it should be greater than or equal to. So here it is greater than, and so this condition will be satisfied. But converse is not true. Decreasing function may not be strictly decreasing. Now next we take up necessary and sufficient condition for monotonicity. Let fx be any function differentiable in open interval AB. Let fx be any function differentiable in open interval AB, then f is monotonically increasing in AB if and only if f dash x is greater than or equal to 0. F is monotonically increasing in AB if and only if f dash x is greater than or equal to 0. That is, if f is monotonically increasing in AB, then derivative must be greater than or equal to 0. And if derivative is greater than or equal to 0, function must be monotonically increasing. The result is true both ways. It is a necessary and sufficient condition. We can say it is a necessary and a sufficient condition, or the result is true both ways. That is, the converse is also true. F is monotonically increasing in AB implies f dash x is greater than or equal to 0 in AB, and f dash x is greater than or equal to 0 implies f is monotonically increasing in AB. Similarly, if f is monotonically decreasing in AB, then its derivative must be less than or equal to 0 in AB. And if derivative is less than or equal to 0 in AB, then it must be monotonically decreasing in AB. The result is true both ways. The converse is also true. Now note, if in addition to the above condition, that is differentiability in AB, fx is also continuous at the endpoints. That is, it is continuous at A and continuous at B. That is, if fx is continuous in closed interval AB, because fx is differentiable in AB, differentiability implies continuity. If function is differentiable in open interval AB, it will also be continuous in open interval AB. So if function is differentiable in AB, continuity in AB is assured. So this will mean fx is also continuous at the endpoints. So additional information is only at the endpoints, and continuity in AB is known from differentiability. So we can also write this as fx is continuous in closed interval AB. But extra information is only being provided for the endpoints. continuity in open interval is assured from differentiability. So if in addition to this condition function is also continuous at the endpoints, then we can conclude fx is monotonically increasing or decreasing in AB. If the function is continuous at the endpoints, then this will mean it is monotonically increasing in closed interval AB. And here it will mean fx is monotonically decreasing in closed interval AB. If fx is continuous at A and B, then we can replace this by closed interval AB. Let fx be any function differentiable in AB. Then f dash x is greater than 0 in AB implies fx is strictly increasing in AB. And f dash x is less than 0 in AB will mean fx is strictly decreasing in AB. But the converse of this is not true. That is, if fx is strictly increasing in AB, then it is not necessary that f dash x is greater than 0. fx is strictly increasing in AB does not imply f dash x is greater than 0. So converse is not true. fx is strictly decreasing in AB, it does not imply f dash x is less than 0 in AB. For example, let fx be equal to x cube. Now graph of this function is, a rough graph of this function is and from the graph we can see that it is a rising graph. So this function is strictly monotonically increasing. No two values are same. The graph is never horizontal, it is strictly rising. It is strictly rising. Nowhere it is a horizontal graph. So this graph is strictly monotonically increasing. Therefore fx is equal to x cube is strictly monotonically increasing. But f dash x is equal to 3x square. F dash x is equal to 3x square and f dash x is equal to 0 at x equal to 0. Therefore, in any interval A, B, including 0, fx is strictly monotonically increasing, but f dash x is also equal to 0. So strictly monotonically increasing will not mean f dash x is greater than 0, because here the function is strictly monotonically increasing but f dash x is equal to 0. That is, f dash x is not greater than 0. It is not greater than 0. It is equal to 0. So converse of this is not true. Now we are going to take up some questions based on monotonicity. Now to solve these questions, we can divide the solution into these steps. First will be find f dash x. Second will be leave positive definite terms. You find f dash x, and if there are any terms which are positive definite, you leave them, because sign of f dash x does not depend upon such terms. So you can leave them. Then put rest of the term equal to 0. After leaving the positive definite terms, the remaining term you put equal to 0. Let x be equal to a1, a2, a3 be the roots of this equation. There can be any number of roots, but I am considering for understanding I am taking only 3 roots. So you can divide the interval a b given in the question into the following intervals: a1, a2, a3. So break the interval into a1, a2, a2, a3, a3, b. A1, a1, a2, a2, a3, a3, b. And to interpret the results, you can make use of the following table. Write the interval here, find the sign of f dash x in this interval, and draw the conclusion. If sign is greater than 0, function is monotonically increasing. And if sign is negative, less than equal to 0, then the function will be monotonically decreasing. So you can write the conclusion here. Now we take up the first question on monotonicity. Find the interval of increase and decrease of this function. Now we are given fx is equal to this much. And what we do is first we find the derivative. So this is equal to, differentiation of this is 6x square minus 6x minus 36. Differentiation of 7 is 0. So what we get is 6 is common. We get x square minus x minus 6. And this is equal to 6 into x square. Factorize this. Now 3 2s are 6. So we will have minus 3x plus 2x. Sum of these two is minus x and product is minus 6. So this is minus 6. So this is equal to 6 into x is common and we get x minus 3 plus 2 is common, we get x minus 3. So this is equal to 6 into x plus 2 into x minus 3. Now the second step is, first step is find the derivative, and second step is leave any positive definite terms. There are no positive definite terms in this, so we put this equal to 0. 6 into x plus 2, if there are any positive definite terms, we will leave them and put the rest equal to 0. But there are no positive definite terms, therefore we put this directly equal to 0. So this is equal to 0. And this implies x is equal to minus 2 and 3. So we will break the number line into, this is minus 2 and this is 3. So we will break the number line into 3 intervals: minus infinity to minus 2, minus 2 to 3, and 3 to infinity. Because this function can only change its sign at these points, this and this. In this interval, sign will remain same. From here to here, the sign will remain same. From here to infinity, the sign will remain same. So we break this number line into these 3 intervals and check the sign of the derivative. We make the following table. It has 3 columns: interval, sign of f dash x in this interval, and what is the conclusion. Interval, sign of f dash x, and conclusion. So first interval is minus infinity to minus 2 and sign of f dash x. Now sign of f dash x is same throughout this interval. So instead of checking the sign in the whole interval, you can check the sign in only one point. One point in this interval is minus 3. So sign of f dash x at a minus 3. Minus 3 plus 2 is minus 1. Minus 3 minus 3 is minus 6. Minus 1 into minus 6 is positive. So this is positive. First I will find the sign in all the intervals and then draw the conclusion. The next interval is minus 2 to 3. Minus 2 to 3. Now in minus 2 to 3, take any point. Any point in minus 2 to 3 is 0. At 0, f dash x is, this is 0 positive, this is 0, then this will be minus 3. That is positive into negative is negative. So this will be negative. And third interval is 3 to infinity. Now in 3 to infinity, any point is 4. 4. So put 4. 4 plus 2 is 6. 4 minus 3 is 1. So this is positive. So this is positive. Therefore conclusion will be, since in this interval f dash x is positive, therefore fx is monotonically increasing. In this interval it is negative, therefore fx is monotonically decreasing. In this interval it is positive, therefore fx is monotonically increasing, and therefore fx is monotonically increasing in this interval, that is minus infinity to minus 2 union 3 to infinity, and fx is monotonically decreasing in this interval, that is minus 2 to 3. Now fx is a polynomial. This is a polynomial, and polynomial is continuous everywhere. Since fx is a polynomial, therefore it is continuous everywhere, and therefore we can include the endpoints in monotonicity. We can write fx is monotonically increasing in minus infinity to minus 2 closed interval. This endpoint can be included, and this will be 3 to infinity. We can include these endpoints, and fx is monotonically decreasing in minus 2 to 3. This is the answer. Fx is continuous, therefore we can change these brackets into square brackets, include the endpoints. Now the second part is fx is given to be minus 2x cube minus 9x square minus 12x plus 11. You can see the side sheet. Now what we do is we find the derivative f dash x. This will be minus 6x square minus 18x minus 12. This is equal to minus 6 is common. We have x square minus plus 3x plus 2. This is equal to minus 6 into x square. Now product should be 2 and sum should be 3. So we break this into 2x plus x plus 2, and this can be written as minus 6 into x common, x plus 2 plus 1 is common, x plus 2, and this is equal to minus 6 into, this is one factor is x plus 1 and the other is x plus 2, x plus 2. Now there is no positive definite term, therefore we put this equal to 0. Let minus 6 into x plus 1 into x plus 2 be equal to 0, and therefore x is equal to minus 1 and minus 2. So we break the number line into, this is minus 1 and this is minus 2 and this is minus 1. So we break the number line into 3 intervals: minus infinity to minus 2, minus 2 to minus 1 and minus 1 to infinity. We make the following table. First column is interval, second is sine of f dash x, and third is conclusion. Now first interval is minus infinity to minus 2. Second is minus 2 to minus 1. Third is minus 1 to infinity. Now sine of f dash x. Sine of f dash x in this interval is same. In this it is same. In this it is same. So we find the sine of f dash x at a single point. Single point in this interval can be taken as minus 3. So put minus 3. So minus 3 plus 1. Minus 3 plus 1 is minus 2. Minus 3 plus 2 is minus 1. So minus minus plus and 1 minus more. So it will be negative. So this is negative. In minus 2 to minus 1, take any point. Minus 1.5. Minus 1.5, this is negative. Minus 1.5, 2 minus 1.5 is positive. This is negative, this is positive. So negative into negative is positive. And in minus 1 to infinity, take any point. Say 0. So 0, this is positive, this is positive. So this is negative. And for continuous functions, it is generally, if it is negative in this interval, it will be positive here. It will be negative. For continuous functions, there will be alternate plus minus signs. So conclusion is fx is monotonically decreasing in this interval. It is positive, therefore fx is monotonically increasing in this interval. It is negative, so we say fx is monotonically decreasing in this interval. And therefore we can write the conclusion as fx is monotonically decreasing in minus infinity to minus 2 union minus 1 to infinity, and fx is monotonically increasing in this interval minus 2 to minus 1. And since fx is a polynomial, it is continuous everywhere. It is continuous everywhere. And therefore we can include these endpoints, change these round brackets into square brackets. That is, fx is monotonically decreasing in minus infinity to minus 2 union minus 1 to infinity, and fx is monotonically increasing in minus 2 to minus 1. Now we take up the next question. Here fx is given to be x plus 1 whole cube into x minus 1 whole cube. What we do is we first differentiate this function. F dash x is equal to first function into differentiation of second, x minus 3 whole square, and differentiation of inner function is 1, plus second function into differentiation of first. Differentiation of first is 3 into x plus 1 whole square, and differentiation of inner function is 1. So we can write this as, what we see is x plus 1 whole square into x minus 3 whole square is common, and we are left with 3. 3 is also common. So we are left with x plus 1 plus x minus 3. That is 3 into x plus 1 whole square into x minus 3 whole square into, this will be 2x minus 2. 2x minus 2. 2 is common. We have 6 into x plus 1 whole square into x minus 2 whole square into x minus 1. Now these two terms are positive. These two terms are positive, and therefore the sign of f dash x, does not depend upon these terms. These terms always remain positive. So what we do is we put x minus 1 is equal to 0, that is x is equal to 1, and break the number line into, this is say 1. So this will minus infinity to 1 and 1 to infinity. These two intervals will be there. This is interval, sign of f dash x, and conclusion. First interval is minus infinity to 1, and next is 1 to infinity. We will leave the points at which these two terms are 0. So I will tell you how to include these points. So this will be minus infinity to 1, minus infinity to 1. Take any point, say 0. In 0, this will be negative, and sign does not depend upon this, therefore this will be negative. So this is negative. And in 1 to infinity, take any point except these two, 2 and minus 1. Let me mark them here also, 2 and minus 1. These 2 points have to be excluded. This is 1 to infinity. 1 to infinity except 2, say 3. So 3, this is positive, and these two terms are positive. So conclusion will be fx is monotonically decreasing, and here fx is monotonically increasing. So conclusion will be fx is monotonically decreasing in minus infinity to 1, excluding the point minus 1, and fx is monotonically increasing in 1 to infinity, including this point. This is 2. These 2 points have to be included. But fx is a continuous function, everywhere function, being a polynomial. Fx is a polynomial. Fx is a polynomial. Therefore, it is continuous everywhere. So we can include these points, and therefore fx is monotonically decreasing in minus infinity to 1, and fx is increasing in 1 to infinity. We can include these points and the endpoints. We can include a finite number of points at which f dash x is 0 can be included if fx is a continuous function. So this is the conclusion, and you can try this yourself. You can try this. Now I take up the next question. Find the interval of increase and decrease of these two functions. Now in first part we are given fx is equal to this much, and we have to find the intervals of increase and decrease of this function. What we do is we first find its derivative. F dash x is equal to 4x cube minus 24x square plus 44x minus 24, and derivative of 21 is 0. This is equal to 4 is common, we have x cube minus 6x square plus 11x minus 6. Now we have to factorize this polynomial. you can factorize it by the methods you have already studied. I will factorize this using synthetic division to give you practice of synthetic division. I will factorize it using synthetic division. This will give you another method of factorization. The traditional methods you already know. So what we do is at x equal to 1, f dash x is equal to 1 minus 6 plus 11 minus 6, that is 0. The first step is we find a root of this polynomial, and we know integral roots are divisors of the constant term. So when you want to find the roots of this equation, you only try the divisors of this term, that is plus minus 1, plus minus 2, plus minus 3, 4 is not a divisor, leave it, 5 is not a divisor, leave it, and 6. So you will try only 1, 2, 3 and 6. So I put x equal to 1, we got the root. If it is not a root, then we will try x equal to minus 1, plus 2, minus 2 and so on. Now what we do is we divide this polynomial by the factor corresponding to this root, that is x minus 1, for which we use synthetic division. Write the quotients first. 1 minus 6, 11 minus 6, and 1 is the divisor. So method is write the starter first. 1 is the starter, 1, multiply 1 with this and place under the next. Add, multiply by this, place under the next and add. You can see the side sheet for keywords. Keywords are multiply, this is the starter, multiply this with this, place under the next and add. Multiply by this, place under the next and add. Multiply by this, place under the next and add. This is the remainder, and this will give the quotient. Now you can calculate the degree of the quotient from here. This will be the constant term, constant x square. Or you can also calculate the degree of the quotient by, we are dividing this by x minus 1. So we will get the quotient of degree x square, a quadratic. So what we get is x f dash x is equal to 4 into x minus 1, factor corresponding to this is x minus 1, into the quotient is x square minus 5x plus 6. These are the two factors. Now this can be written as 4 into x minus 1 into. Now we have to factorize this. Now we know 3 2s are 6 and 3 plus 2 is 5. So we write this as x square minus 2x minus 3x plus 6. This is equal to 4 into x minus 1 into x is common, x minus 2 minus 3 is common, x minus 2. So this is equal to 4 into x minus 1 into, this is one of the factors, x minus 3 into x minus 2. So these are the factors of f dash x. Now what we do is leave any positive definite factor. There are no positive definite terms, so we will put this equal to 0. Put 4 into x minus 1 into x minus 2 into x minus 3 equal to 0. We get x is equal to 1, 2 and 3. So we divide the number line into these intervals. This is 1, this is 2, this is 3. So So we will divide the number line into these intervals: minus infinity to 1, 1 to 2, 2 to 3, and 3 to infinity. We enter whole information in the form of a table. First column is interval. Second is sine of f dash x. And third is conclusion. Now first interval is minus infinity to 1. Second is 1 to 2. Third is 2 to 3. And fourth is 3 to infinity. Now sine of f dash x changes only at these points. It will remain same throughout this interval, same throughout this interval, and it will be same in this interval and in this interval. So what we do is, for finding the sine of f dash x in this interval, I will put one point in this interval. Say x equal to 0. So put x equal to 0. This will be negative, negative, negative. So three negatives will make negative into negative is positive, into negative is negative. 1 to 2, 1.5. 1.5 minus 1 is 0.5, positive. 1.5 minus 3 is negative. 1.5 minus 2 is negative. So this is positive, negative, negative. So overall sign is positive. And in 2 to 3, say 2.5. So overall sign is negative. And in 3 to infinity, take any 1.4, 5, 6, you can take any 1.4. So 4 minus 1 is 3. Positive. 4 minus 3 is positive. 4 minus 2 is positive. So overall sign is positive. Now we write the conclusion. Since f dash x is negative, we will say fx is monotonically decreasing in this interval. And f dash x is positive, therefore fx is monotonically increasing in this interval. And here fx is monotonically decreasing because f dash x is negative. And here it is positive, so fx is monotonically increasing. So we will say fx is monotonically decreasing in minus infinity to 1 and 2 to 3, and increasing in 1 to 2 and union 3 to infinity. Therefore fx is monotonically increasing in 1 to 2 union 3 to infinity, and fx is monotonically decreasing in minus infinity to 1 union 2 to 3. You can see the side sheet. And since fx is a polynomial, fx is continuous everywhere, and therefore we can include the endpoints. Therefore fx is monotonically increasing in 1 to 2 union 3 to infinity, and fx is monotonically decreasing in minus infinity to 1 union 2 to 3. This is the answer. In these intervals, it is strictly monotonically increasing, strictly monotonically decreasing. But here it is monotonically increasing, monotonically decreasing. If you want to know the intervals in which the function is strictly monotonically increasing or strictly monotonically decreasing, these are the intervals. Because in these intervals, f dash x is strictly greater than 0. In these, it is greater than equal to 0. So in these it is monotonically increasing, monotonically decreasing. Here it is strictly monotonically increasing, strictly monotonically decreasing. And we know a strictly monotonically increasing function is also monotonically increasing. A strictly monotonically decreasing function is also monotonically decreasing. So we can write monotonically increasing and monotonically decreasing. But a monotonically increasing function may not be strictly monotonically increasing. And monotonically decreasing function may not be strictly monotonically decreasing.